I'm going to talk about the project, which is performed by the joint force of Institute Jaroslav Černi, who is in charge with project leader is Professor Mila and they are providing samples and rationalizing our results. And my laboratory at the Faculty of Technology and Metallurgy is involved in analytical chemistry mostly. So my topic will be mainly analytical chemistry. We have, in the last more than 3 years, we have been monitoring pesticides and pharmaceuticals in Danube and tributes. And as our target compound, we have chosen 15 insecticides, 15 pesticides, mostly insecticides, one fungicide, carbendazim, which was mentioned here a number of times in the morning session, and a few herbicides. And as far as pharmaceuticals are concerned, we have chosen 20 compounds, antibiotics, sedatives, where the most important sedative is carbamazepine. It was mentioned in the morning session as well. We have used a group of analgoantipyretics where there is one original compound and we are analyzing 2 metabolites of metamizole, which are very stable in the environment. And recently we have introduced some cardiovascular drugs because they're very frequently used in Serbia. The procedure of sample preparation of all our samples is based mainly on solid phase extraction. We are using Oasis HLB cartridges, and after preconditioning of these cartridges with a mixture of methanol and water, we are introducing 100 milliliters of sample, rinsing the column with methanol, drying it, and then eluting our analytes with methanol, evaporating the solvent and reconstructing the solution with 1% methanol. So in this step we are gaining 100 times pre-concentration of our analyte. As far as the analysis is concerned, we are using Finnegan LCQ Advantage machine, which is the basically liquid chromatograph, high pressure liquid chromatograph, which is connected to the mass spectrometer, and our mass spectrometer is very special construction. We are using electrospray as an ion source, and then we have the ion trap as mass spectrometry analyzer, and in this ion trap we can, in the cavity of this ring electrode, which is sliced on my slide, we can keep the ions for reasonably long time, and we can either then record the mass spectrum when we eject the ion, or we can do something else. We can select a single ion species of a particular M/Z ratio and keep only targeted ion species in the ion trap. And I'll give the example of that analysis on one example of the surface water. This is a typical total ion current chromatograph which we obtain from surface water samples. And the little peak here on the shoulder of this big one is carbendazim insecticides, which is very commonly present in the environment. What we do then, well, if you look at the mass spectra in this red region, we can see the peak 192, which should be painted red. And this peak is protonated molecular ion of our analyte. This spectrum is pretty useless for quantitative analysis, and therefore the next thing we can do, we can select the targeted ion, and then we can record what's called selected ion chromatogram, which is the trace in red on my slide. But this spectrum is, what we have here is a relatively high baseline. That means that we have a permanent leakage from our column of something that is that corresponds to the mass of our analyte. And when we this chromatogram is very unsensitive, because signal to noise ratio is 5:1, and because of that we can do something else. That's MS analysis, or tandem mass spectrometry analysis, which was mentioned this morning. We can collide this molecular ion, quasi-molecular ion of our compound with the gas in our ion trap, and we get, as a result of that process, we get bond cleavage, loss of 32. This is the green peak on my mass spectrum, and we can now plot the selected reaction chromatogram, which is the lower chromatogram on the slide, and we have now signal to noise ratio more than 10:1, and this chromatogram is very good for quantitative analysis. For the compounds, for some compounds found in real samples, we usually do a third step of mass analysis, and we confirm the presence of a targeted compound through two consecutive reactions in the ion trap. And this is how the result that we obtain looks like. Each peak for each compound is a result of MS analysis, and it is selected reaction that was monitored. As far as the samples are concerned, Jaroslav Černy had picked a number of sampling places in Serbia. Most of the samples were taken from Danube, and some of the samples were taken from Danube tributes, Tisa, Sava, Morava, and Pek, very close to the confluence to the Danube. And in these 3 years, we have done a lot of analysis, a lot for us, over 100 samples. And these are the results for pharmaceuticals. The most commonly, do we have a pointer in here somewhere? No. And do we have the mouse? I can point out. No. Okay. So the most common compounds of pharmaceuticals that we can find in water are metabolites of metamizole, 4-FAA and 4-AAA, and carbamazepine, which is the general problem with very persistent compound. And then we have some other compounds like trimethoprim, lorazepam. The presence of pharmaceutical is not connected to the season, because we have here spring, summer, autumn, and winter. They randomly appear in surface water. And I have here these two gray rows are the samples of the groundwater, where we have also found metabolites of metamizole and carbamazepine. So this is this table summarizes the results on pharmaceuticals and pesticides that are found in surface water and groundwater, and in between those two layers there are sediments. So this year we have started doing sediment analysis, and the first we worked out that a lot of pharmaceuticals and pesticides are really stored in the sediments in a riverbed. Then we have started a study of adsorption of pharmaceuticals and pesticides on the sediments that were brought to us by Laušević Institute. And these are these are the real curves that we are getting. Here just the points are connected, and the adsorption isotherms are for carbamazepine, clopidogrel, which is cardiovascular drug, and metoprolol, which is also cardiovascular drug. Carbamazepine we can find everywhere. We can find it in surface water, in sediments, in groundwater. Clopidogrel is found so far mostly in sediment, and metoprolol we have never detected in the samples from Serbia. So the point is, carbamazepine is relatively, sediments have relatively low affinity towards carbamazepine, a bit higher towards clopidogrel. This is concentration in water, and this is concentration in soil. And metoprolol is very strongly absorbed on the sediments. And these are the samples that we are getting from Laušević. They were taken at the riverbed here, or from the wells. This is material of when they're drilling the wells very close to the river sampling sites. And this table summarizes the affinity of a particular drug depends on composition of the sediment. And these are the sediments taken from different depths in sediments taken from different depths in equilibrium after 48 hours with 50 ppb solution of the pharmaceutical. And what can we see from this slide is that basically there are two types of pharmaceuticals. For metabolites of metamizole and clopidogrel, for example, the highest absorption is observed on a riverbed. So riverbed is really the best barrier for pharmaceuticals, between pharmaceuticals and aquifer. On the other side, carbamazepine and metoprolol, for example, they're very poorly absorbed on riverbed. They're much better absorbed on clay and sandy sediments, and carbamazepine and metabolites of metamizole are the most commonly found compounds in Serbia. So if we look at this table, we can see that metabolites of metamizole are very poorly absorbed on the riverbed, and after that they travel undisturbed towards the aquifer almost without any adsorption on the soil, and therefore they tend to move with water. On the other side, carbamazepine is relatively poorly absorbed, but it looks like carbamazepine is an anti-epileptic, and it is given to the patients permanently. And it is very old drug, so we think that the environment is almost saturated with carbamazepine, and it's all present in most of our samples. Beg your pardon? 2 minutes. What we wanted to look at now is what is the fate of those absorbed compounds on the sediments. And we have performed the experiments where we have done the absorption from water and desorption from the same sediment in the mixture of organic solvents. And the striking thing is that, for example, for carbamazepine, which is poorly absorbed, we can recover 91% of that pharmaceutical, and for the rest of the pharmaceuticals, we can recover only between 20 up to 40%. That means they are either degraded, chemisorbed, or destroyed in some other way on their way to the aquifer. And in conclusion, I would like to say that pharmaceuticals and pesticides are present in surface and groundwater in Serbia. Therefore, the aquifer in Serbia is endangered. And the thing that I think we should do here in this country is to control the waste disposal, which we don't do at the moment. We should build wastewater purification plants, which are very rare in Serbia, and that's the only way to protect the aquifer. And I would like to thank my group. They're all ladies, and here in the audience, most of them, so I hope you'll have a chance to talk with them about our results. Thank you very much for your attention.